Hello everyone, welcome to the class. So today we will begin with a new topic. This is called new parameterization, and more generally we will look at different parameterizations of neural networks. I will describe in a minute what that means and why that is useful. So, so here's the setup. So you have a neural network, and just to be precise, let's define it like this. So we have a bunch of weight matrices. WL, which are in I don't know, some dimension, n by d. Yeah, written by n, let's say. Oh, okay. So yeah, so if we have like a deep neural network, let's say, so it is parameterized by a bunch of weight matrices, and yeah, so to be precise, let's say you have the first matrix is in n by d, the other matrices are in n by n. So think of your vector being fed to the neural network. So that is some d-dimensional vector being fed. Yeah, and then it goes through these layers. Yeah. So the first matrix here is n by d, and the others are n by n. So yeah, that's what this means. And then you have some non-linearity phi, which is called activation. Yeah, so with these parameters, you can define the function of the neural network as so function computed. So yeah, so I guess all of you know this, but this is just to set things up. So you just pass the input through these layers one by one, and each layer is just a matrix multiplication. That's all. And after every matrix multiplication, you apply the non-linearity. So you multiply, you apply a phi, you multiply, you apply a phi, and so on. That's it. And okay, sure. Okay. Yeah. So to be more precise, you say that your the function is given as follows. So f of some input z, so it's I don't know, it's called z or something. It's called z, right? Yeah. So f of z is w l plus 1 xl z. So xl z is the output of the after the lth layer. So so in this setup, at the end there is no nonlinearity. So at the end you have just this matrix multiplication. WL plus 1, and then we get the output. So yeah, so no nonlinearity here, and XLZ is the output at this point. Just before this, XLZ. Ready. See. And now you can define this XLZ recursive. So you just say, yeah, so define it in two steps. So you say, so you get an output by first multiplying with a matrix. Just call that H. So HL plus 1. Z is the linear thing. this one XL Z. So that's after matrix multiplication, and then you do one more step of the nonlinearity. So XL Z is phi Z. So yeah, that defines the entire function we're computing. Great. Now, what is the meaning of a parameterization now? So here, of course, parameters are W and yeah, and phi, but think of phi as fixed, so it's not a parameter, right? But the question is that suppose I want to study what happens to the function computed by this network and what happens to the training dynamics as I make the network bigger. Yes. So the question is that as I make it bigger, how should I scale the W's? Yeah. So yeah, I guess that's really the question. And and the question of finding the right parameterization is the question of finding the right scaling. So we just write it here. So it's like the big question. As we scale the NN. Oh, sorry. What is the correct? Whatever correct means, it's not going to clear what it means. It's what scale of the parameters and maybe also hyperparameters. So for example, when you initialize, you will typically sample the weights from some random distribution, right? Sample each weight independently. But the question is that as you scale, how should the variance of this distribution change? So, like, what should be the typical size of this weight? So, what should be typical weight size? Or yeah, basically, what should its standard deviation be? Standard deviation or variance. Yeah, so that's the question of finding the right parameterization. So, and why am I calling it parameterization? Because if you have a sense of what it should look like, so let's say, so as an example, suppose you say that, suppose you believe that a weight should look like 1 over root n times some constant. So suppose this is your belief, then ideally you should train the network on just this constant. Right, because if you have a sense of what a scale should look like, then might as well fix the scale first. And then you just do gradient descent and whatever else you want on that constant. So therefore, then the scale 1 over root n then comes out, and then the parameterization while training becomes this constant. So the trainable parameter becomes this constant. This is in some sense the correct trainable parameter, like the most natural trainable parameter. Most natural trainable parameter. Yeah. So hence by identifying the correct scaling, you can identify the correct parameterization for your training. And right now it's just about weight, but the same thing is true for hyperparameters. So same analogous stuff for hyperparameters, like the learning rate, for instance. Cool. Okay. So that's the big question. And now let's think about, okay, why is this question important? Of course, it kind of looks important, but also let me from a more principled perspective. Sorry. Okay, so motivation. Okay, so there's a bunch of motivations. So the obvious theoretical motivation is that maybe you want to study the large bit limits. And why is it useful? Because a lot of behavior gets simplified when you take a lot of neurons. Okay, so yeah, so simplify the behavior and helps you understand what's going on. Understand the dynamics. Yeah, but like and even better practical motivation, which also ties in well with this theoretical motivation, is that in practice, new networks are becoming bigger and bigger. So NNs are becoming bigger, and therefore this last bit limit is actually not a bad approximation. It gives you insight into what's going on. Yeah, gives insight. And even like more crisply, understanding this can help you do what's called hyperparameter transfer. So this can help in hyperparameter transfer. Okay. So and understanding this hyperparameter transfer was the original motivation for the work of Gregorian or mu parameterization, which is the title of this slideshow. So yeah, so now I'll talk a little bit about what hyperparameter transfer means and why it's useful. Okay, so as you might recall from previous discussions in the class, setting hyperparameters like learning rate requires you to know many things. It requires knowledge of of all kinds of stuff, of many domain objects, right? So for instance, in the class, you need to know things like the number L, which is the smoothness parameter, how far you are from the optimum, and all kinds of stuff. And for how long so it requires knowledge of many objects. And that was there in a very simple setting. Everything was convex and nice, often and time. And even if it was non-convex, you had all kinds of nice properties. But here for neural networks, and especially in practice, estimating these objects is very hard. So these are like very expensive to estimate in practice. So here is the plan for mitigating this. So yeah, so how can you set hyperparameters in a nicer way without having to estimate everything? So here is the plan. So you first train a smaller model. And yeah, and a smaller model, because training is cheap, you can try all hyperparameters. You just do grid search. Yeah, just do like grid search on hyperparameters and find the optimal one. And then you just scale the model up. But now when you scale up, then the question becomes that how do these hyperparameters scale? Yeah, so clearly, if you can answer this correctly, then you can obtain like orders of magnitude improvement on your cost, because you don't have to try so many hyperparameters on your big model. So yeah, that's the killer question at hand here. And yeah, so let's start this. So here is the extremely informal setup for this part of the course. So what we will cover. So we will cover, okay, first lecture today and Thursday. We will do just intro to different parameterizations. So we consider a bunch of parameterizations and see what happens, just to like play around and get a feel. So and here by different parameterizations, I mean that different scaling things. So you scale as 1/√n or 1/n or something. So different scalings. Yeah. And then we will do a more precise theorems on large bit limits. That hey, so if I take a certain parameterization and I go to infinite width, then yeah, then what limiting behavior will I get? So we'll try to do some more precise theorems, and finally we will get to the punchline. So we will get to the correct parameterization, and then yeah, some stuff here. Correct. Sorry. Parameterization. So I don't know how much of this stuff we will do rigorously, but let's see how much rigorous. But yeah, this is roughly the plan. And yeah, and I guess all of this is based on tensor programs by Yang et al. And the previous works. And previous work is also like kind of important, because I think Yang's work builds on a lot of previous work on large width limits. And today I will describe some of that work. Okay, great. So yeah, that's like a very rough outline. Yeah, I guess we'll try to do as much exciting as possible, but let's see how much we can do this. But yeah, first two classes will be like test. Yeah, intuition building for all of these things, and yeah, and setting the lay of the land. Okay, great. So yeah, so let's start with some toy examples and this right. So here's like the formal setup for a parameterization. So all parameterizations that we will look at in this course will be what are called ABC parameterizations. Or they will be like similar to ABC. So what is ABC parameterization? So ABC are just three numbers. Yeah, three constants. And these may be indexed by the layer. So more precisely, this would look like, okay, more precise. Okay, it's called ABC. But more precisely, it looks like ALBL union C. Okay. So for each layer, you have two constants AL and BL, and you have another constant C, and these constants control the scale. And how do they control the scale? So you uh, parameterize each weight WL as n to the minus AL W little l. Okay. And you initialize each entry of the so each entry here WL, so each trainable parameter, so WL alpha beta. So alpha beta means the alpha beta is entry of that matrix. So this you take from a standard Gaussian, not standard, but mean zero Gaussian with variance n to the minus 2 BL. Standard deviation is n to the minus BL. And finally, use your learning rate for stochastic gradient descent as eta times n to the minus c. Okay, so in a nutshell, so AL tells you the scale that you plug in front of the LS layer. BL tells you the standard deviation at initialization at the LS layer, and C tells you the learning rate of the HAD. And as you might kind of get from this picture, so there is some symmetry in this, because if I because my total weight is a product of n to the minus AL and essentially some n to the minus BL term which will come from the standard deviation. So in some sense you can adjust the ALs and BLs by keeping AL plus BL constant. So yeah, there's some symmetry inside this. So yeah, so it doesn't make any real difference, but just that maybe in some papers you might see a different ALBL, in other paper you might see a different ALBL, but maybe it's the same thing because of the symmetry. Just like keep in mind while reading stuff. Okay, great. So now I want to give some examples of these ALs and BLs and which have been used in practice. So this is more of a factual thing than anything conceptual. So here's some examples. There is what's called the NTK or neural tangent kernel. Also called NTP for neural tangent parameterization. So here you have A1 equal to 0 and actually we'll make a table. I'll do better. Should do that. It will make a table. So here's a table of some stuff which which has been seen before. This is NTK or NTP. So A1, AL, or at least two PL, C. Okay. So for NTK, AL, A1 is 0. So you don't do any scaling at all in the first layer. And yeah, and after that you do AL equal to half. And DL equal to 0. Okay. C equal to 0. So this is called the NTK parameterization. Then what's called the mean field mean field neural tangent. Okay. So the mean field is already defined for one hidden layer. I mean, of course, you can define for anything, but it's only studied typically for one hidden layer, usually. So here you have A1 equal to 0, A2 equal to 1, and yeah, and BL is 0. So this is just 0. And C is minus 1. Okay. So only on A2 because typically you only do this for one hidden layer. Yeah, and it's like remind you. So what does this mean? So this is the coefficient of n to the minus. Okay, so your weight scales like 1 over root n. Height scales like 1 over n. And in this case, like yeah, and this is actually big. So here you use learning rate of C. This is a mistake. I think this is fine. Yeah, okay. So yeah, and finally, let's look at what's called the standard parameterization. So that's the one which is kind of most often they use in practice and available in most libraries. So standard parameterization for SP. Okay, so this is given by here is 0 for all other things. I don't know what's this. Yeah, so L is 0, BL is half for L at least 2. So B1 is 0 and BL is maybe we should have made 2 rows. Okay. Yeah, let me make 2 rows. Okay. Yeah. So BR is half, which basically means that your standard deviation looks like 1/10. That's standard deviation. Yeah, and your C is 0. Okay. Yeah, so the only thing which are typically used, they have been seen before. And yeah, and we have these names like neural tangent kernel for a reason, and we also talk later why it's called, why the word kernel is present here. And yeah, and where the word we field comes from. So we'll see in detail later. Yeah, and the standard is written because in most libraries with people will use this the parameterization that will be there. Great. Okay, so now let's do like a toy example and some preliminaries. It's a toy example, and let's look at the standard parameterization. The purpose of this example is to kind of show that the standard parameterization is not a very good thing. So yeah, and then we kind of motivate why these things are important to study. Okay, so before we can fully understand SP, let's first set up some notation. So okay, first of all, for the toy example, I will look at only one hidden layer neural network, and I will also assume that the so input output dimension is also one. Let's say. So let's say so. Okay, so d equal to 1 basically. D equal to 1. And output dimension.
The screen is blank. Like they are not shared a screen on.
Oh.
On YouTube.
Yeah, thanks. Well, okay. I guess
Okay,
I think I forgot to do it here.
so
Okay, then we can start now. I guess it's pretty useful. I think अभी तक we have been just
notes are there.
errors are there. And yeah, so but yeah, thanks for catching.
Even how you log in.
No, remember log it. Just know that.
I don't know how to answer the call because login for something.
Sorry.
I don't know how to answer notice this because.
Oh, yeah. Maybe just checking the page, see what's happening. 4, 5, 7, 6, 7.
Audio. No, 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 you're not able to. The same thing, the arrow, or the couple.
Yeah, thanks. Okay, so yeah, so that's now, since it looks very simple, now you can simplify the parameter as well. So let's call f of zeta as v x y1.
Okay.
Yeah, v x zeta.
What is the Google?
Okay, so this is what it looks like. So so here v and u are your variable parameters. And let's say your v. Okay, so what are the dimensions of v and u? Okay, can someone tell me? You are not bold. So remember,
This and plus one. Because Z is just your input Z is just one element.
yeah, input one dimension. Yeah, great. So you n cross one, and this should be the other way around, obviously.
Yeah, we should do one first.
Yeah, very good. Yeah, and this looks like n to the minus say, AV times V. And this looks like n to the minus AU times U. Okay, so here, and I should call it VI or something. So little v is your vector essentially. So these are vectors. So now, as before, think of v and u, little v and little u as the actual triangle parameters. Yeah, and as usual, we will sample every entry in this vector. So every entry v alpha from the distribution to bv, and every entry u alpha yeah. So that's what it looks like, and for learning rate is theta times. Great. So yeah, that's the shutdown. Okay, so now we can write down our gradients and stuff to understand what's going on. So I'll use this notation of Yang. So where he summarizes the gradient of the function with respect to some object at a point zeta as d that object. Which is like myself to write. So okay, so let's say, okay, so with this notation, what is dx zeta? So that's the partial derivative of the function with respect to x. It's easy. Yeah. This is just right. Yeah. Yeah, and now you can just use scale rule and to figure out everything else. So dh zeta. Yeah, so now you just plug this twice, so you take your dx zeta and you do matrix multiplication. Things like a constant, use the symbols for matrix multiplication. So, yeah, that's the chain rule. And dv zeta. Okay, so what about v? What about little v? So this is very easy, right? So again, you can use chain rule. Minus av, yeah, x dx zeta. Oh no, wait, it's this is x zeta. And du zeta and to the minus au dh zeta times zeta. Yeah, good. Yeah, okay. So this can help us figure out gradient descent. Okay, so now write down what gradient descent is. So SGD updates. So for now, let's not worry too much about the expectation stuff. So in SGD, you sample some quantity which in expectation is a gradient. But for now, let's not worry about all that. So this is for example. So not getting into all that. So simplified, yeah, like so super simple, yeah, simplified and made. Yeah, so you ignore the randomness. So then you have ut plus 1 is ut minus the learning rate times gradient, right? So okay, so what's the gradient here actually? So remember, what we wrote there was the gradient of the function. What we actually care about is the gradient of the loss. So yeah, so you look at the loss gradient. Yeah. So L dash of the so you take the function value and you take the true output. So yt is your true output and ft is your observed.
We have to see it. No, right?
Yeah. So here I'm being a bit sloppy. So I'm not writing the z.
Yeah.
So suppressing the z for covert letter. Pressing z.
No, see this FT is okay, but this Y is this is your training data, right? So this
Yeah. So yt from training data.
but it's the same for is it the same for all times? 1 x Oh, I guess you're doing HDD styles. You're using different data points for different levels.
Yeah, exactly. So I'm going to simplify the thing out.
Yeah.
Yeah, it's a bit. Yeah, so this is not toy stuff. So we're not doing any real thing. This is just like get a sense of how things happen. So because right now we only put about the scaling. So the actual thing is not of interest right now. So I can just write anything as long as it's the right scale. Okay, so something will just like the loss, and then to be minus. Why? So let's recall. We look at the previous slide. Yeah. So yeah. So now we're seeing how capital U updates, right? So capital U is entity minus A times E. So look at whatever update happened on U on little U, and just transfer that to capital U by multiplying by entity minus A. Yeah, and the same goes for B. And yeah, maybe like just to be a bit more complete. So maybe we can write down the full loss gradient. So the loss gradient of the loss, right? That's the thing which actually matters. Gradient of loss is of theta y times your vector dv zeta v theta. So say I'm taking gradient of the loss with respect to the both parameters c1 v. Writing the whole gradient. But chain rule is what it looks like. Yeah, and that's how you got those two equations. And yeah, just to be a bit more concise, let's call this loss derivative as phi t. That looks better. Yeah, yeah, and now you can just write down everything with these notations. So now we're ready to play. All the good stuff is ready. So let's see. So for there's a relativity equal to 1. So okay, so what do we want to know, right? So let's say you want to know how your activations have evolved. Okay, so your activations were X and H, remember, little X and little H. So I want to know how they're changing. So uh, I want to know what delta X1 zeta looks like. Where by delta X1 zeta I mean how much it has changed. So this is by this I mean X1 zeta minus X0 zeta. So this is a quantity of interest. So let's say you understand this. So yeah, the one step, what's going to happen? So let's see. So yeah, so remember we first get H and then we get X. So let's first figure out how H changes, then we plug and figure out how X changes. So delta H1 zeta, how much does it change? So that is just minus AU by 0 zeta T0. Why? Because if you recall, I think should have some kind of running slide which has the derivatives. I don't know how to do that. Maybe I can write them on the board. Huh? That's why the board is useful. Let's write them. Is it a talk? Yeah. So for convenience, here are the derivatives. And here, sorry, let me try it here. So f of zeta was okay, that was the function for zeta was 3x zeta. That was the last layer. Then x zeta was p of x zeta and x zeta was u zeta. So that's for the parameterization. And your D matrix was there was small drugs. N to the minus AV B was in R minus AU and by 1 and yeah. So entries of V came from to BV. So various plus minus to BV and these are few. Okay. The learning rate was so there was setup. And what were the gradients? So with the notation, so gradient of the function f at theta with respect to something is denoted as d that's something theta and d x theta was v d h theta was d x theta British multiplication. Yes. Okay, so yeah, oh, this is enough. Let's see. Okay, great. So now with this, what's your derivatives? Yeah, yeah, we are ready to write what our thing is. Okay, so what is delta H1 zeta? So that's just just write it in 2 steps. This is H1 theta minus H0 theta. Okay. So and let me also write down the gradient descent. I think that's yeah, I think that will be useful. That's how you will figure this out, right? So how does your capital V capital V change? So you okay, so your delta ut okay, so, no, it's kind of confusing. So ut plus 1 minus ut is minus chi t and to the minus ut and vt minus vt plus 1 minus vt minus v minus av. Okay, this should be useful. The chi t is your lost gradient, lost derivative. Chi t is prime. And here we are being a bit sloppy, and so yeah, so we can ignore the expectation. So really, so there's a matter. We're not ready for that. Okay, so yeah, so with this, yeah, simple. Now I'm going to work out what delta H1 this should be. Yeah, how will you do it? Anyway, simple.
This is U1 thing minus U0. U1 minus U0 is just instant.
Yeah.
So it will be Z times minus factor minus A would be good.
Yeah, exactly. Yeah, exactly. Yeah, good. So you just yeah, as I said, sorry.
All this there should be an eta.
So I guess eta will come when you go to like the end. So at the end of the chain rule.
No, in your gradient step there should be an eta. Right?
Oh yeah, here.
Yeah, ut plus
yeah, there should be eta.
There should be eta.
Yeah.
It should be eta.
Yeah, should be eta. Yeah. Good catch. Yeah. Yes, I'm not sure why it's putting it up there. Oh, you're right. There should be an eta here. And yeah, eta to the eta times n to the minus c. Really there.
Yeah.
Fine. Cool. Okay. Okay. Yeah. So now I guess we'll just multiply with whatever you said. So it will be minus eta to the minus c times n to the minus au by 0 eta du 0. Yeah. Makes sense. Good. Yeah, and then you can just write it out a bit more. The minus c times but also confusing. Theta theta 0 theta let's just use the chain rule again. Here. But it's not theta 0 anymore, it's a theta. Yeah, so I think this is this equation. Great. And now we just work it out. This is minus eta into the minus c times 2 by 0 theta square. Yeah, and then we do like one more step. So we can now plug the dh from here.
3 times 3 times.
Yeah. B times. We multiply. Like. Yeah, so this is what it is. Maybe I just
Capital V acceleration.
sorry.
This V is a capital V.
Yeah, this is a capital. It's not clear. Cool. Great. Okay, so yeah, and now let's plug in our values of a and the variables.
Capital V should be the one step 0.
Yeah, okay, that's also very good. So we should write
That's it with n minus av times small v.
Yeah, sure. One could do that. So you can also do that. So minus AV times small v0. Okay, there. Okay, so yeah, and now I try to understand what this looks like for our privatizations. Let me cheat a bit and make some space on this slide. So let's remove this. Can I shake this? Oh yeah, I can do this. Great. And I can move this up. Yeah, in fact, I'll just write this here. So this is just minus eta into the minus c minus 2 au minus av by 0 zeta square v0 what is multiplied 5 prime 0. I will shake this. It's a neat trick. Maybe it's ugly to read. Okay, great. This is what it is. Okay. Now let's plug in our puts numbers. See what happens. So let's do the first one, which is NTK. For NTK, what do you call it? Yeah. So the first layer is here, and then it's like a half, right? And the base was 0. It's 0 also here. So let's see. So what do you get? You get yeah, exactly into the minus half, and then yeah, some stuff. And yeah, and remember see the b is also 0. Everything is like a constant. So yeah, so this looks like essentially this is theta. Sorry, this is theta 1 over root n. So that's the moral of the story. And yeah, and therefore your so that's the case for h, and similarly also for x, because remember from this equation x1 zeta minus x0 zeta looks a bit like is roughly like 5 prime h0 zeta matrix multiply, right? So yeah, so therefore it should be of the same order, and therefore yeah, so basically everything is of order all the activations are order 1 over root, theta 1 over root n. And then you can kind of, again, this requires a leap of faith, but yeah, but you have 1 over root n behavior across all time steps. So, so as long as the time steps are not too many, again, pretend n is very large, so large that number of time steps is incomparable to n. It will say 1 over root n. Good. Okay, so now let's check what happens in other things. So, what about the mean field? Let's recall what numbers were there. So here, A1 is 0 and A2 is a 1 and B is a 0 and C is a minus. So this active. So let's say it happens now. So now it should be so you get a plus 1 minus 0 minus 1. Yeah, and that's the constant. That's theta of 1. Yeah. Okay, and what about standard parameterization? Just also check that. So in FP, everything is 0 and the P is a half. So now the P is a half. Then how do you think of this? So now,
So D0 is theta of n domain.
yeah, exactly. So then it should be 1 over root n.
Stuff in front is 0, but yeah, D0 is theta of 1 over.
Yeah.
Yes.
Yeah. FP also it will be yeah. Good. Okay, so yeah, now we know how to do stuff. And okay, so now look at the properties of what's going to happen. So okay, so this is what the update looks like. So now what next? How do you understand what will happen? So like in the remaining time, I want to just focus a little bit on the standard parameterization to to get a better sense. So yeah, so let's look at SP and let's be like even more. Let's simplify a bit more. Simplify even more. So let's say we assume that phi is identity. Then okay, so the key argument is so key point is that H H yeah Yeah, so basically your F would have roughly IID Gaussian coordinates of variance theta. Why? Let's see. So again, let's go back to the previous slide, right?
H0 is theta 1. When you update theta h are theta 1 by 10, so they are very small.
Yeah, exactly.
So you don't change much.
You don't change much. Yeah, that's the whole point. Yeah. And in fact, you can now say a bit more precisely what's called the you can figure out what's called the kernel of the uh, features of the learned features in a sense. And you can see that the kernel will not change. So let's see that. Okay, so let's find the kernel. So to find the feature kernel. P theta xt theta transpose xt simple by n. Okay. So what you're saying is saying that you take your learned feature, which is xt at time step t, for some and you think about it as a function of your input theta. And then we define this kernel function as it's quantity here. And now the punchline is that this feature kernel does not change much. In NTK or SP, but actually, but it does a mean field. So okay, so let's see why. So here's theta over zero transpose. Sorry, I think I'm not very good at writing the jam word. Should probably I don't know, let me shrink this a bit. Sorry.
Does it have street feature?
Yeah, yeah. So we'll do this. Yeah, I think I probably. Yeah, I think I erased it. Okay, sorry, I'm not this. Right again. So now to get a feature color. So FT. Yeah, what's happening? Slightly copies. Okay. Yeah, makes sense. Where by delta xt I mean xt at whatever input minus xt at 0.
X0, right?
Yeah. So x0 at that. So this is what I mean by delta. The delta of something is that thing at t minus that thing at 0. Cool. Okay, so now let's see what this is. So this is so again remember my the points that my delta xt will look like 1 over root. And therefore, yeah, so as you correctly observed, the second two terms will be like really small.
Last term will be even smaller.
Sorry?
The last term will be even smaller.
Even smaller, yeah, exactly. So the whole thing will look like order 1 over root. So order the initial term per root.
Yeah, initial term plus 1.
Yeah, so your color change basically. So your delta ft. This is like yeah, so this is like this. So that's a,
F0 is order 1. F0 is theta 1.
yeah, true. So yeah, as you see now, so indeed. So so yeah, that's like not a nice thing. Whereas because you want the neural network to learn something, right? And if this color beta is not changing much, then that's kind of an indication that you're not doing much. And yeah, whereas as you can imagine, for mean field, this would change because there these data look like order. Whereas so this is the case for MTK. Theta 1 for main field. Yeah, so that actually. Okay, great. So so they all want to say that. So the question of today's class is that by writing these gradient updates carefully, it is possible to understand the behavior for large width or your whatever ABC parameterization you choose, and you can get a sense of how much things will change, whether they will blow up, whether they will shrink. Yeah, just to these calculations. So yeah, and then the next part we will see how to use calculations to get more insight into what happens, and then we will understand also the mu p characterization and the mu p parameterization and why it is important and useful. Great, thanks. By the way, here I said that we actually will be IIT, but IIT, but actually here you don't need it. I probably need, but for what we'll do next time. For this, you don't need it actually. This is true. So, yeah, so maybe I'll just erase it so that people don't get confused. So you don't need yeah, you're trying to zero these things. Just works. You actually don't have to even say this. Yeah, I think it just works from here. Right. Extra.